I want to go to page 23 and then fill out this row. Write the row above the nth row using this NK notation. Okay, good. Alright, so the next one's N2 and then N3, etc. Dot dot dot. At some point you get NK. Yes, okay, NK. And then NK plus 1. And then the one before is NK minus 1. And then this is N minus 1. Just filling a few terms like that. Okay? Alright, so write down this row. And we're going to discover some pattern about this row of the Pascal's triangle. Okay, so do this first. And after you do this, we're going to establish some formulas. Okay, so we'll learn that from the Pascal's triangle, both of these equal to 1, as shown here, n0 equal to n equal to 1. And also the symmetrical property is that this one equals to this one. The symmetrical property n1 is same as n minus 1. The second one same as the second last one. The third one same as the third last one. Or this, which is this one, nk equal to n minus k. This is the symmetrical property that we've seen earlier. Okay, good. So these are the two well-known results. The next one we're going to look at is not as well known. So what I want to do is put in a line that came directly before the nth row to establish this complicated formula. So I want you to write down the row before that. So let's drop this off. Okay, click on that. Alright, so write the row before that. That will be n minus 1, 0, right? The row before this. And then write a few terms like before. Let me write it properly. N minus 1, 0. This will be n minus 1, 1. N minus 1, 2, right? The Pascal's triangle. And then n minus 1, 3, etc. And then I want you to write a few above. This will be n minus 1, k, n minus 1, k plus 1, n minus 1, k minus 1, right? And the row before will have one less term from the row below. So the last one will be n minus 1, n minus 1. That's where it stops. That's the last one. Okay? Right. Check out what I wrote on the board. See if it matches yours. So everything matches. The bottom number matches. But the top number will be one less than the previous row, than the next row. Okay? Now, where does this come from? This is just the result of the Pascal's triangle. That if I add any consecutive terms, that gives me this, right? So if I add these two, it gives me this one, right? So if I add these two, it gives me this. So which gives me this amazing result, okay? Which you should memorize. I think it's a good result to memorize. And it's not hard to memorize because it's a result from the Pascal's triangle. This is the additive property of the Pascal's triangle. And you are expected to know how to prove it as well in the test. So how do I prove it? Now, this is not a proof. This is just a way to demonstrate where the result comes from the Pascal's triangle. If we add any consecutive terms, it gives you the next term on the next row. And to prove it, we have to use the formula for nk. So we can prove it algebraically. Just prove it algebraically. And that result is examinable. Okay. So what we do is we start from the right-hand side. Okay, start from the right hand side. n minus 1, k minus 1 plus n minus 1k. That. And then we continue. We're going to write n minus, now use the definition. Now let me write down the formula next to it. nk equals to n factorial k factorial n minus k factorial. Okay, like that. So what we do is we're going to use the result n minus 1 factorial over k minus 1 factorial, and then you subtract these two, n minus 1 minus k minus 1 factorial, like this. Okay, and then plus, do the same thing, use the definition, n minus 1 factorial k factorial, and then find the difference, n minus 1 minus k factorial, like that. Okay, and then I will want you to simplify this further. N minus 1 factorial k minus 1 factorial, and then you go n minus 1 minus k plus 1 factorial. And the other one, just leave it as it is. Alright, but I want you to write n minus k minus 1. So swap the numbers around. So just write this. Okay? And then you'll notice that the minus 1 and 1 get cancelled. Right, so we'll just simplify this first. We don't do anything special yet. We'll just write it like this. N minus 1 factorial, k minus 1, and then k n minus k factorial. And then we're going to combine them in our next step. Everything stays the same. Right. Okay, like this. And then what we do, we're going to make them the same denominator. And then temptation just, maybe, let me just use this pen. So if you make a common denominator, maybe you just go like this. This is k minus 1 factorial. Now don't write this down yet, so you write this. And then this one, you times by n minus 1. Yeah, that will get very complicated, right? You get too complicated. So if you do it like that, that will be too complicated. So it's better to look at what's inside the factorial. So let's look at, let's compare these two. Which one's the bigger one? The k factorial or the k minus 1 factorial? The k factorial. So we're going to unroll this one. Let's unroll it. Okay? And also we're going to unroll this one, the bigger one. So you write n minus 1 factorial, the k minus 1 factorial. Let's unroll the one I underline in green. N minus k minus 1 factorial. Unroll this. Okay? Same thing for the other one. We're going to unroll the k factorial into k, actually, yeah, k, and then k minus 1 factorial. Okay? But the second one do not change. Okay, so we got that. Yep. Now we have to make them the same denominator. Now it's clear what we have to multiply. So comparing the first one with the second one has an extra k that the first one does not have, so give a k to it. And comparing the second one with the first one, we see that the second one doesn't have a n minus k, but has everything else. So it can minimize the amount of things you multiply. That will simplify the algebra. Now they have the same denominator, isn't it? So now, because they have the same denominator, let's write them as a common denominator. And we'll get to our result very soon. So let's write it as a common denominator. Right, like that. And then write k n minus 1 factorial plus n minus 1 factorial n minus k. And then what you do is you can simplify the denominator and factorize the numerator. Let's factorize the numerator. So I factorize the common factor. These are common. So I take that out, n minus 1 factorial. And then k plus n minus k. Like that. Over the bottom, I want you to combine these two to be k factorial. Combine these two to be n minus k factorial. And then you'll notice that the k and the minus k can cancel, which you end up to be n minus 1 factorial over k factorial n minus k factorial. And then these two will become n factorial. So you end up with nk. So this is the exact formula for nk. Okay, and now I'm going to write equal to nk right hand side. Nk right hand side. Okay, let me enlarge this so you can copy it down. Right, that's the whole page. Okay, have a look. And then we'll move on to some other proof. Alright, think about the proof. It's very long, so I'm going to practice this again at home by yourself because I think the proof is examinable and there's get you to practice a lot of skills in this part of proof. So you should practice this again at a later time. So make sure you practice again by yourself. Alright, good. Alright, once we do this, we're going to move on to the next page. Alright, make it a bit bigger so it's easier. Do some more proof. Alright, we're going to move on. Next page. Okay, next page is ask you to find the value of A, B, and C. So this is pretty easy. You just write A equal to 3, B equal to -4, C equal to 5. That's an easy example. And that relates to the next example we're going to do. Hopefully you've done this type of proof. So let's do that, comparing coefficients. So we can prove this. Relate back to the Pascal's triangle. Remember, now this is the result from the Pascal triangle because if I write the row, so if I write 2, 0, 2, 1, 2, 2, and then this is 3, 0, 3, 1, 3, 2, remember that if you add these two, it gives you that. That's the result of this, right? Now, this, we're going to prove it using this formula by writing 1 plus x cubed as 1 plus x times 1 plus x squared. Now, how do I do this? We're going to compare coefficients. So this indicates to us this is the x squared term, isn't it? So let's write the x squared term. So what we do is Actually, to do that, what we do is we're going to expand it. Let's do the left-hand side. Left-hand side is, when you expand, is 3, 0, 3, 1x, 3, 2. So you should be able to do that pretty quickly because it's pretty easy to write now. Write this expansion. Let me rub this off. Okay, good. All right, and then we're going to do the right-hand side. Now, to do the right-hand side, we're going to write down the expansion. RHS equal to 1 plus x, 1 plus x squared. And you're going to expand the 1 plus x squared, 1 plus x times 2, 0, plus 2, 1x, plus 2, 2x squared. Like that. Yep. And now I want you to expand this. 1 times this, 1 times that. So times, so you go 2, 0, plus 2, 1x, plus 2, 2x squared. Okay, expand the 1, then expand the x. I'm going to do it in maybe green. Right, plus 2, 0x, plus 2, 1x squared, plus 2, 2x cubed. So we got this expansion. After we expand, we collect like terms. Keep it as 2, 0 first. The two like terms are these two. So you write it as plus 2, 1, 2, 0, x plus 2, 2, 2, 1 x squared plus 2, 2 x cubed. Okay, we expanded both the left side and the right side. Now, what's the purpose of this? I could match coefficient of both sides, just like we did with example 17, that the coefficient of both sides must be equal. So if I compare the coefficient of x squared and the coefficient of x squared, it must be equal. That's how we get this formula, right? So the coefficient of x squared must be equal. So you write comparing the coefficient of x squared from both sides, we x squared from both sides, we can say that 3, 2 must be equal to this. And that's how we prove this formula. As you can see, we did a lot of unnecessary work because we don't really need the other terms, isn't it? We just need the 3, 2 term and the x squared term. So what we do is this, we can have a faster way. So, faster method. And you're allowed to use the faster method in tests, and you're encouraged to use the faster method. So how does the faster method work? You just have to explain what you do. Alright, so what you do is, you say that the x squared term from left-hand side is. It's very important that you explain so that you're not just writing down the result. The x squared term is 3, 2x squared. Right? And then you write x squared term from right-hand side is. Now remember what the right-hand side is. 1 plus x, 1 plus x squared. Right? So what you do is, you have to show your clear working. You have to physically do 1 times the square term, right? 1 times the square term, and then x times the x term, right? To show how you got this term, which is equal to 2, 2, 2, 1, or x squared, right? And now we can just match the coefficient, and then you just write equating the coefficient of x squared from both sides. We get, therefore, 3, 2 is same as 2, 2 plus 2 is 1. Yeah, so can be done. You should try the next page proof. Exactly the same. Right, exactly the same. Have a try. Example 19. Okay, so go to the next page when you are ready. Try this one, is exactly the same. Okay, so for now, just have a look, see how I write it. Very important that you explain yourself very clearly, so you're not just copying down the result. You have to explain how you get the result. Okay, all right, go to the next page, have a try. The next one. So how do I know which term to look at? That gives you a clue. The 2 means the x squared term. Okay, try the x squared term and do exactly what I write. And then we'll go through the solution soon. Have a try before we go through. Yeah. All right, good. Hopefully you've done. Give you a minute. Okay, all right. Let's go through this. So clearly this is the x squared term, so you write x squared term from left-hand side is 5 to x squared, right? Because that's 5, so 5 to x squared. And then you write x squared term from right-hand side is. So you have to show the expansion 1 times the x squared term, which is 4 to x squared, because the highest power is 4. And then you have to go x times the x term, which you can simplify to be 4 to 4, 1, factorizing the x squared out. And once you do that, you say, therefore, comparing, equating the coefficient of x squared from both sides, we get 5, 2 equal to 4, 2 plus 4, 1. Okay, so it's pretty easy. All right, the next one you could try by yourself. The videos on Google Classroom that I recorded last year, so you could check your answers there. So that's from Google. You can check video from Google Classroom. Okay, you should try to do it by yourself. And then the next page one, which is also on Google Classroom. Now remember this, we did the proof earlier. That's a third way of proving. So you should also check video. Okay. All right. What else we go through? Now we're going to go through some more identities today. So go to page. Actually, it's all right. Okay, let's go through this. Again, these are all on the videos are on Google Classroom, but I want to go through this page. Just some examples. I think we've done them already. Okay, so we're on page 28. Go to page 28. So far we have already established these three identities, that this is one, symmetrical, and the one we just did recently, just today. And now we're going to prove more identities. These ones are more complicated, where it involves a series of terms, that the sum of this equal to 2 to the power n. That can be proved easily using this expansion. So you always start with this expansion, and there are three types of proof. We're going to go through some of each type. We're not going to go through all the examples because the video is on the Google Classroom. We've done it on Friday already. Let's go through this one. Why do they add up to 2 to the power n? So let's do this. So we start off with the expansion equals to n0, n1, n2, x squared, plus dot dot dot. You don't have to write everything, n x power n on page 28. And then what we do is, it's very easy. All you have to do now, if you look at it, all the x are gone. They look the same. All the x are gone. So how do you make them gone? Substitute x equal to 1 onto both sides. Onto both sides. And if you do that, the x will be gone. And then you will have 1 plus 1 to the power n. That will be n0, n1, n2, and n. Yep, like that. Now, what's 1 plus 1 is 2. 2 to the power n. Now we'll prove the result. Right? That the sum of these binomial coefficients gives you powers of 2. And you can check that it actually works, because like if you try number 1, 3, 1, if you add them, what do you get? You get 8, which is 2 cubed, isn't it? If you do 1, 4, 6, 4, 1, what do you get? If you add them, that'll be 5, 10, 16, which is 2 to the power 4. So all this rule is a result about Pascal's triangle. That if you add all the numbers on a row, then Pascal's triangle, you get powers 2 to the power of that number. Okay, the next one, you probably have seen it before on Friday. I'll leave it to you. You can watch the video. But you will note that when there's an alternating, what do? You substitute x is -1. That will result in alternating signs. So I'll leave it to you. You should watch the video and finish it off. And how about the next one, C? We'll talk about it briefly. Now, when it comes to this type of proof, whenever the question has a sigma notation, I want to rewrite the question because it's confusing. It's too short. It's too abbreviated. It's hard to interpret it. So what you need to do is rewrite it. So write nc0, 2 to the power 0, plus nc1, 2 to the power 1, nc2, 2 to the power 2, dot, 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 ncn, 2 to the power n. So rewrite the result. So this is what you try to prove. You try to prove this. Now, how do I prove this? Again, you start with the expansion. Your first step is start with this expansion, x power n equal to... Now, because they use nc0, you should also use the same notation as them. So you should write nc0 plus nc1x plus nc2x squared plus dot 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 ncn x power n. Okay? So you have to match your notation with their notation. And the exam question can use either notation. Make sure you use the correct notation. And when you write it underneath, clearly you can see what to substitute into x, isn't it? What should x be? X must be 2. So you write x equal to 2. So you write 1 plus 2 to the power n equal to n0, nc0, nc1, 2 plus nc2, 2 squared plus ncn, 2 to the power n. And you have to simplify that, you get 3 to the power n. We write it again. NC12 plus NC2 square, NCN2 power n. Okay, so result proven. Alright, okay, so that's the first type of proof, substitution. Sometimes substitute 1, substitute -1 if it's alternating signs, sometimes substitute 2, sometimes substitute anything. So you have to look at the pattern. The next type is differentiation and integration. We're going to do a bit of each. How do I know differentiation was used? We have to look at the example to see how it works. So we're going to look at example 24. Okay. And then there's these ones. We'll do one from there. And then we'll skip. Okay, good. All right. Hopefully you're ready. Okay. Second approach is differentiation. Now, let's expand this first. Now, have a look at this. You get 2 and 3 and etc. Okay. What we do is, let's start with the expansion. N0 plus N1x plus N2x squared plus ... and x power of n. Actually, that's equals to 1 plus x power n. Okay, we're on page 29. So what we do is, if we try to substitute, for example, x equal to 1, it doesn't give you this because the numbers change all the time. What if I substitute x equal to 2? It will still not get this, right? Because it keep getting, the numbers keep increasing. When this sort of things occur, you're not just substituting x equal to 1 or 2 or 3, you have to differentiate it. That's how the numbers are created, from the differentiation. So we have to differentiate both sides of the expression. So when, remember, this is a 1, so when you differentiate it, it's 0. So you have to maybe write down both sides, differentiate both sides. So what you get 0 plus n1 plus 2 times n2x, right, differentiate x squared, plus ... n times nn plus subtract the power by 1. Also differentiate the right side and 1 plus x power of n minus 1. So that's how the consecutive numbers are created, by differentiating. And then there's no x, means that you just substitute x equal to 1. So it's a very easy proof. When you substitute 1 to power anything is 1, so that's gone. And you get n1 plus 1 to power n minus 1, which is 2. Okay, so you get n times 2 to power n minus 1, which is the result. Okay, good. Okay, good. After we do this, we'll look at another approach. Same approach, differentiating. Now we have to integrate. Integration will give you another formula. So hopefully you're ready. So we're going to go to the next page. Probably you've seen the type of proof already. Okay, so let's move on. Right, now when you see fractions like this with increasing denominators, that's a result of integration. Now let's write down, again, your first step is to write this down, n0, n1, x plus n2, x squared plus n3, x cubed, plus ... nn, x power of n, equals to, yep. Okay, good. All right, continue. You get 1 plus x power of n, and you're going to integrate both sides. That's where the fractions are created. So let's integrate. So this is n0. It's a constant, so you write n0x plus n1 x squared, but you put a half in front. 1/3 n2 x cubed. Plus ... Can't be bothered with integrating that, so we'll just leave it out. And then we go 1 over n plus 1 and n x power n plus 1, right? Equal 1 plus x power of n plus 1 on n plus 1. But you must plus c. It's an indefinite integral. Plus c. And you have to work out what that c is. And it's actually not easy, not hard to work out what c is. Substitute x equal to 0 onto both sides. Why 0? Because you make things disappear, isn't it? Because you substitute 0, things just get, they just, when anything multiplied by 0 is 0. So you get 0 plus 0 plus dot 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 0 equal 1 plus 0 to the power of n plus 1 on n plus 1 plus c. And what do you get? You get 1 over n plus 1 plus c is 0. Therefore, c equal to negative 1 over n plus 1. Okay? Because 1 to the power n plus 1 is 1. Now, update your formula. So you update n0x plus n1 half n1 x plus x squared 1/3 n2 x cubed plus dot 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 1 over n plus 1 and n x n plus 1 equals to 1 plus x power of n plus 1 on n plus 1 minus 1 over n plus 1. And then you just substitute x equal to 1 on both sides. That will get rid of the x. So then you substitute x equal to 1. And you get n0 half n1 plus 1/3 n2 plus dot 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 1 over n plus 1 and n equals to 2 to the power n plus 1 minus 1, make a common denominator, which is the result they asked you to prove. Okay, alright, so these proof you have to memorize, knowing what to do, and when to integrate, when to differentiate, and we'll do maybe we'll do a summary after this. We'll do a summary. No, we'll do one more example, then we'll do a summary. Okay, so hopefully you all got it down. Yep, all finished. Alright, again, that's also on Google Classroom, the video. Okay, alright. Alright, let's move on. So the next one, again, if there's a sigma notation, write it without sigma. So to do this, you go R0. So basically, we write this as N0 minus 1 over 2 and 1 plus 1 over 3 and 3 and 2 plus, and then minus 1 over 4 and 3 plus dot dot dot, and the last one will be minus 1 to the power n over n plus 1 and n, that equal to 1 over n plus 1. And when you see the alternating sign, again, to prove it, you integrate this expression n0, and then you substitute x equal to -1. That gives you the alternating signs. Okay. Right. So again, the video is on the Google Classroom, so you could have a look. So check video. All right. What else are there? And then we'll do another proof. So this is the second approach. The last approach is compare coefficient. We'll do one example, and then you look at the video on Google Classroom. Okay. All right. Let's move on. Next one. All right. So this one is the one we've seen earlier, using this result to prove this. So you have to compare coefficients. The last bit is equating coefficients. Now, which term do we look at? How do we know? Yeah, which term? How do I know? Do I calculate x cubed term? or x power 4 term. Yeah, x power 5, this one, that's the clue. So if I x power 5 term, so you write it down. So you write x power 5 term from left hand side is 4, 5, x power 5. Right, that's your first step. And then you do the other one, x power of 5 term from right hand side is, now this one you have to do some work. You write 1 plus x squared, 1 plus x power of 10, write it as 1 plus 2x plus x squared, expand the perfect square. Then you get to see what to do, because you're going to do, you have to, there's 3 ways that can be created. You have to go 1 times something, 1 times the x power 5 term, 10, 5. And then you have to go 2x times the, actually I forgot, x power 5. 2x times 10, 4, x power of 4, like that, plus x squared times the x cubed term, like that. So there are 3 ways of creating the x power 5 term on the right, which you can factorize out. 10, 5, 2, 10, 4, plus 10, 3. All this to the power of x power 5. And then you just say, therefore, equate coefficient of x to the power 5 from both sides. We get, what do we get? We get 12, 5 equals to 10, 5 plus 2, 10, 4 plus 10, 3. Right, so these are the all 3 approaches you could get in an examination. So remember which type to use, and then we'll do a summary. There's other 2 hard examples I encourage you to try and watch the video. So try by yourself, and watch video to check, and watch video. Okay. All right, good, all done. And then next page also, next one's a little bit harder. Again, I want you to have a try and watch the video, try and watch video, try and plus watch video. And then the last one's also very difficult. You should also have a try as well. And then we'll go to the summary. Let's do a quick summary, and which is not on last year's video. Last video I didn't do a summary. So we're going to expand. So we're going to know that the expansion will be n0 plus n1x plus n2x squared plus dot 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 and n. And need to know the kth term is, tk equal to nk a to the power of n minus k b to the power of k, which is on the formula sheet, but you should memorize it. So this is very important. Helps you to do a lot of questions. And we need to know what a term independent of x is, which is the constant term. Oh, sorry. All right, which is the constant term. Constant term, and this is also a term with the power 0. Okay. And then we also need to know some formulas about NCR. NCR equals to n factorial over k r factorial, which is not on the formula sheet. Not on the formula sheet. I forgot. No, not on the formula sheet. So you have to memorize n minus r. And then you also have the symmetrical property. That's the symmetrical. We're on page 35, symmetrical property. And then we also have this 1 that equals to n. And we did that earlier, n minus 1, r minus 1. Okay, and you should write all of this using the new notation: n factorial, k factorial, n minus k factorial, and then you should write this one again: n minus k equal to n k. Write it clearly: n minus k. And then this one will get n0 equal to nn equal to 1. And then this one will be n1 equal to n minus 1 equal to n. And this one you get nk equals to n minus 1, k minus 1 plus n minus 1 k. Right, so you should be able to interpret them in both notations. I don't know why I wrote this again. Okay, so let's write it again. It doesn't hurt to prove again. n1x plus n2x squared plus dot 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 nn. And this is important. So once you've expanded this, it allows you to prove the following formulas. So use that to prove all these formulas. Okay. So how do I prove the first one? You just have to substitute x equal to 1 onto above. And when you see alternating sign, you do substitute x equal to -1. And when you see powers of 2, you substitute x equal to 2, right? And then this one, when you see consecutive, what do? You differentiate both sides. Differentiate both sides. And then substitute x equal to 1. Right? And how about this one? You integrate both sides. When you see fractions, integrate both sides. Right? And then substitute x equal to 1. This is the second approach. And the last approach, you have to compare coefficient. Compare coefficient of x power 5 from both sides. So these are the three approaches. Alright, so think about what to do. So that's the summary of all. I think I did some of this in the video as well, so you could look at it later. Alright, good. So let's continue with your homework today. So I'll just finish there.